So this is the Particles Homework Booklet question 39. We told that the diagram below, which we'll have a look at the moment, shows electrons being fired at a polycrystalline graphite target in a vacuum. The electrons are emitted from a heated cathode and pass through an accelerating PD. The inside surface of the far side of the chamber is coated with a fluorescent material that emits light when the electrons release their energy to it. And we're given a mass of an electron and Planck's constant, which for some reason we're only given to 2 significant figures when they're on the datasheet to 3. I guess this question predates the datasheet. So here are those diagrams: heated cathode there, accelerating PD, 4,500 volts, evacuated tube, which we seem to have lost the label for. There's the fluorescent screen. We've got the graphite target in there, and here's that same fluorescent screen viewed front on. We're given the speed. I think a question you would want to look out for in the exam would be to be given an energy in electron volts. But anyhow, on this occasion, we're given a speed and we're asked to calculate the debris wavelength. Yet again, straightforwardly, H and M from the formula booklet, V from there. My V is only to 2 significant figures, so I'm going to give my answer to 2 significant figures. The next question is asked to draw the pattern on the front view. Follow those instructions. It asks you to draw the pattern on the front view. So some kind of dot in the middle and rings, preferably a little bit more circular than I've managed to draw mine. Bit single mark. I think that would probably do the job. And to explain why the pattern suggests that electrons have got wave-like properties. So we've done the sketch. Explain why the patterns. Because it appears to be a diffraction effect. So diffraction is a wave-like property. Remember when we saw diffraction before, it was from a single slit and we got a bright central band and then it went dark and then bright bands and dark bands. The reason this is circular rather than those kind of band patterns is because it's polycrystalline, so we've got different crystals of the graphite in different orientations, so we're kind of getting the bands in all different orientations, which kind of spins around and gets that circular pattern. It may be worth mentioning in there that we're getting some significant diffraction because the wavelength is approximately equal to the atomic spacing. And then we're asked to explain one aspect of the experiment that suggests that electrons have particle-like properties. Unusual question that, in that we're usually talking about the particle-like properties of electrons in the photoelectron effect and the wave-like properties of electrons in electron diffraction. But it makes sense to think back about the sort of the classical view of these things. So what is in there in the question that suggests that the electrons are behaving in a particle-like way? Well, we're told about, or we think about, the charge on the electron. So having charge is a fairly particle-like property, and we need them to have charge in order that they can be accelerated by the electric field. Another view would be to thinking about the electrons carrying, individual electrons carrying energy onto that fluorescent screen to cause those excitations, which means that as the electrons in the fluorescent screen drop back down to their lower energy levels, they can emit the light that allows us to see where the electrons hit. I think I'd probably focus on that one. I think that's nice and neat and tidy. And that is the end of the Particles Homework Booklet at question 39.